I think you started this in Calc 1 where you found area under the curve, and then you kind of redid it in Calc 2 and generalized it and found out all kinds of other stuff. So the area under the curve is going to be given by an integral between a and b of some function. So what happens here is that we want to translate this information into the parametric equations that we have. So we can kind of look at this as a direct translation where y is equal to f of x, our original function y is equal to f of x, and then we take a look at the relationship between x and y and t. And because now t is our parameter that's dictating how the graph is being drawn out, we can kind of look at that as our new independent variable. Then
is that x to the t of t, or is it x prime?
X prime. So what we're really looking at is the y function and the dx differential and how that's related to the parametric equations x of t, y of t. So since y is equal to f of x, we're looking at the y portion of your parametric equations that's kind of governed by t, or by x, by t. And then the dx is your differential with respect to x. And then you're talking about how that's going to be drawn out. Now this, we can see a lot of weird drawings with parametric equations that are not, functions like a vertical line test type of function. So we have to be careful when we're looking for areas under the curve. We're looking for an area under the curve that is actually dealing with a function that doesn't have, that doesn't overloop each other or something. Similarly, we can also take a look at a function that's along the y-axis. So if you have x as a function of y, then we can find the area under the curve, and the word under here is kind of weird unless you tilt your head to the right, and then it looks like it's under the curve. Then that means we can find the area under the curve where you're looking at this from a sideways point of view. And so we would have the same setup. We would go from C to D or something else. And so the area is going to equal to an integral from C to D of f of y dy. And then we do the same sort of direct translation from parametric to this Cartesian relationship by calling this x of t, right? Because x is equal to f of y. And then calling your dy as y prime of t, dt, if we're looking at the differential. Okay? Yes? Yeah, in this case, it would have to pass the horizontal line test because this is a sideways function. So It has to be either or for us to look at this. We're going to take a look at a different sort of integral where we're finding an area in a different coordinate system that's a little bit more interesting than this, I think. I don't know if this is interesting or even that useful, because if it's something that we can find an area under the curve, we can generally write it as either y is a function of x, or we can write it as x is a function of y. And so doing this in parametric equations is not particularly useful. It's only useful if you have something already defined in parametric equations, and then you can just do it this way. So let's do a quick example of this. Let's do an example where, I don't know, where we can let's do one along the y-axis. That was G just showed me a picture of a homework assignment where I think x is equal to y times y minus 1 squared. Let's take a look at that graph and see if we can find that equation or try to draw this graph. Maybe we should start this on a new page. What am I looking for? I am looking for, yeah. Oops. All right. Let's do the example, and let's try to find out the area under the curve on the positive side of x. So first we have to try to graph this. I think that's one of the key ideas, is to try to graph this. And if we're going to try to graph this, it would be good to know how to graph sideways, kind of. We could look for x and y intercepts. So let's see. How do you find x-intercepts? Set y equal to 0. So, well, if you set y equals 0, this is 0 times something, right? And so x is equal to 0. Does that make sense? That's the x-intercept. Now to find the y-intercept, we set y equal to 0, or x equals 0. And when we set x equals 0, we get 0 is equal to y minus 1 squared. And so this is where we would have y is equal to 0. And with x is equal to 0 and y is equal to 0, we already have that point. And then we have y is equal to 1. And so now we have the other new point that we have is x is equal to 0 and y is equal to 1. So here's the y-intercept. Now, if you know a little bit of graphing, again, this might help if you look at it sideways. What we could do is that we know that x here is a function of y, so this may not pass the vertical line test, but it should pass the horizontal line test. And the other thing to look for is that these are the zeros. That's when x is equal to 0, y is equal to 0, and y is equal to 1. And so what we could do is we could try to figure out what happens for certain values along the y-axis to see whether their x is positive or x is negative. So let's say when y is equal to a negative number, when y is equal to a negative number, like negative 1, I'm going to have a negative, and -1 here would be -2, but you're squaring it, so it'll be positive. So this would be a negative x value. So negative x value would mean it's down here on this side. Again, down if you're tilting your head to the right. Now between 0 and 1, if we put a y value that's positive but less than 1, this is going to be positive, and this is going to be, well, it's going to be squared, so it's always positive. So now we know that this is positive. So now the question is, what happens up here when we put a number like 2 or 5 or 70 that's bigger than 1? So positive, positive. So this is going to be positive again, which means this is going to dip down here and then bounce back up. So this is how your graph is going to look like. Okay? So now that we have that, we can find an area under the curve, or between this graph and the y-axis, where we can set up an integral with respect to y that would go from 0 to 1. Oh, I meant to write this as a parametric equation. Sorry. I just kind of did a pre-calculus problem now. Well, in any case, your parametric equation, this isn't going to be much different. Your parametric equation is going to be x equals t, t minus 1 squared, and y is equal to t. So basically, we're going to change everything into t's. So my x of t is just t minus 1 squared, and my y prime is just going to be 1, and then this will be dt. And then it's the same integral. That's because the parameter, one of the variables is just equal to the parameter, so it didn't really change anything. It wasn't as interesting as the one that I was going to have you guys do. So in any case, from here, I would just integrate this. How would you integrate this?
I would expand it out.
Just expand it out, and then it'll just be a polynomial, probably a third-order polynomial, and then you just integrate one by one, right? So you guys can figure that out. Okay, questions? All right, the last bit of calculus with parametric equations, at least for now, would be finding the arc length. And for that, there's a formula that we can look at. And this formula is it's an interesting formula to to look at. It kind of looks like what does it look like? Square root of something squared plus something squared? Distance formula or Pythagorean theorem. Kind of looks like one of those. And we can take a look at it from either of those points of views without actually doing a formal proof. Let's just say you have a curve from A to B. And the idea behind integrals is to break these things down into small pieces and then add up like an infinite number of them. It's kind of like how I told you how calculators draw. Yeah. So let's take a very rough estimate, and what we're going to do is we're going to find the distance. Maybe let's find the distance between these 2 points. And so you're just finding a straight line. So there's two ways to view this. One way is this is a distance between these 2 points, so that's like a distance formula. Another way to look at this is that, well, it's kind of like the change in x and the change in y. And then Pythagorean theorem says this is going to be the square root of each of those things squared. And so if you imagine taking that same curve and making smaller and smaller points and then more of the same curve and smaller points, it's essentially looking for the distance of these, or if we stick with the Pythagorean theorem analogy, it's just the change in x and the change in y, each of those squared under a square root. So I'm not going to do too much more, but this is the general idea for finding the arc length. In general, finding the arc length is not very easy because the integral that you're going to get automatically has a square root in it. And finding integrals with square roots is already a tall order. And so just imagine if something in here was nice and simple, then it would be nice and easy to do. But if it gets more complicated, then you got to think trig substitution or some other weird integrals that you may have learned or may have not learned. Yeah. Are you going to be revolving them?
Yeah, and finding the surface area or
Only if you want to. We're going to be doing some other stuff with surface areas later on in the semester. All right. So let's see. Let's come up with an example. Yeah, usually when I come up with an example, it's like bad news because it's always screwed up. Let's just make up a function. Might as well screw it all up, right? X equals y equals and then it just becomes really easy now. D cubed. All right. So whatever this graph looks like, let's imagine how this graph looks like. You can actually graph it using your graphing calculator if you want. But let's give it some limits because we need limits to starting and ending points for this. So let's say t goes from where to where? What? I need numbers. -2 to +2. All right, so if we're going to find this arc length, we need the derivatives, and then we just need to put it into this formula. So there's really nothing much to it. So x prime is going to be 2t, y prime is going to be 3t squared. We put into the formula, we got 2t quantity squared plus 3t squared quantity squared. And then we integrate this from minus 2 to 2 dt. And then just solve. Good luck. So you can probably get a numerical value if you punch this into your calculators. If you guys know how to integrate in your calculators and get numerical values. The TI-89s might be able to actually give you the antiderivatives too, but the TI-84s can at least. The T? Yeah. Oh, then it would be U substitution. Wow, so that might turn out to be really easy. Anyways, I'm still not going to do it. So, pardon me? 8 root 7. There you go. That's the answer. You can double check that. I'll leave a question mark here until somebody verifies. I usually want like 2 people to verify. So Frederick says, is that? Uh-oh. Better cross it out. 16 root 10. Anyways, that's a general idea. And then you have an arc length. I think the important part is looking at this formula. Later on, we're going to look at other arc length formulas, and we're going to revisit this arc length formula. And so I'll just remind you when it pops up again. Okay, I think that's it for the... Oh, here's the surface area. Have you guys looked at the homework? Was the surface area problems in the homework too?
For just the first one?
For 10.2.
10.1, I don't think there was any surface area. 10.2.
The surface area is really just another formula. So why don't I put that in our notes?
Are you posting the notes?
I will post the notes. I meant to post it yesterday, but I usually post it right after class. So the notes will be posted, and you guys can view the notes after they're done. So the surface area, this is the surface area of revolution, and all it really does is it takes the arc length and then it revolves it around. And so the arc length, if you look at the, what is it? If you look at this as like a cylinder, and I'm going to draw the cylinder sideways. The surface area of the cylinder, so that's like a can, and then you're looking at the label of the can, so without the top or the bottom. The surface area is what is it, 2 pi r times h or something? And so if you put this in the context of a curve being revolved around a particular axis, and we're not going to do this too much, but if you look at this as a curve being revolved in a particular axis, then we'll take that little piece that we kind of took a picture of last time, and then we're revolving this around the x-axis. The radius, the radial distance, is really just the y value of that curve. And what we're going to do is we're going to sample points with Riemann sum. We're really just sampling a bunch of points between these two x sub I plus 1 or whatever. And then the height here, the r, is the arc length, or the representation of the arc length. So if you imagine your height being the arc length business and then your radius being the y value of this thing, then the 2 pi rh is actually just all part of this formula. Wait, I have that backwards? No, that's right. So the R is essentially the Y value, and then the H is essentially the arc length value. And then you're stacking them up along some T parameter. Yeah?
That's around the x-axis. If it's about the y-axis, is it x instead of y there?
It's X instead of Y here, and then the arc length should still be the same. Correct. Okay. All right. So what I want to do is I want to have you actually try these things, because it's always fun watching me do it. But if you guys don't do it yourselves, then it kind of, you don't get the practice. So instead of actually just giving you a quiz, I was talking about this with Professor Hoffman, and said, you know, people just have to be able to retrieve the information, like almost memorize it, and then we want to try to have a low stakes kind of environment where you're able to do that. So instead of quizzing all the time, I'm going to try worksheets in this class to see if it'll work out. And for this first worksheet, you guys can work with the groups around you, but I think sometime in the future I'm going to shuffle you guys around to work with different people. And then what we're going to do is we're going to work on some problems that's related to what I just talked about, and then have you guys put it up on the board and see how it works out. Okay, so the biggest thing about this is time. We're only going to have half an hour to do this, and so we're going to try to find a way to get the most out of getting this information done. Okay, we're doing the first one. So I'm going to pretend I'm a student and just use the TI 84 instead of using Wolfram Alpha, which is what I would normally do. And the first thing I would do probably is to graph this. And then once I get the graph, I get some idea of how to approach the rest of the problem. And maybe I should have asked you to actually graph it when in the instructions, but I didn't. So let's see, t squared minus 2t for the first one, and then the second one is a square root of t. That's not t. Okay, if I blindly graph and then I'll see something that's kind of hard to see, so I might want to adjust the window. You can do the zoom fit thing, but it looks like this goes all the way up to 2, and this goes -1. So maybe I'll adjust my window going from 0. Maybe I'll go from -1. I don't know if that'll make a difference. -1 or -2 to maybe just 3 for now. My x min is -1. I think it touches -1, so I'm going to go step back just a little bit, -2. And then I don't want to go too far out, so I'll just go to +2. And then my y, I didn't see it go down too far in the negative direction, so maybe I'll just put -2. And then I think it crossed at 2 in the positive side, so maybe I'll go another 3 or 4. All right, so let's take a look at this graph. It looks a little bit better. I can see the intersections over here, and I can see that looking ahead, I wanted to know where this intersects the y-axis, set up a graph to find the area under the curve kind of thing, and using the same limits, find the arc length. So the arc length from these two limits. No? T? Oh. Yeah. I probably make more mistakes than you guys. Look better? All right, good. So now we got the graph. Let's write the equation here. X equals t squared minus 2t, y equals square root of t, and then our graph. So we got some important values to look for. The first thing they ask for is to find the dy dx. So dy dx. I want the derivative of y with respect to t. So this is a 1/2 t to the negative 1/2 divided by the derivative of x with respect to t. This is 2t minus 2. And so you can fiddle around and arrange this any way you want, but I'll just leave it like this and say, okay, this is my derivative. So that's A. B, they want us to find the point on the graph where the slope is -1. And so the slope of -1 has that y equals x kind of slope. And so I know that there's going to be a slope at -1 over here somewhere. And so, oh, slope is +1, sorry. So I want to essentially set this equal to 1. So I have a 1/2 t to the negative 1/2 over 2t minus 2 equal to 1. Right? So I would just multiply both sides. 1/2 t to the negative 1/2 is equal to 2t minus 2. So this is where I think most of you got bogged down with and got stuck with some algebra. And it's not really an algebra problem. I mean, it is kind of an algebra problem, but I think when something like this comes up and you're not asked to find the exact value, I would just go ahead and try to graph this and try to see where they intersect. So I'm going to take out my calculator again, and I have to switch modes because I'm in parametric mode right now. So I want to go back to function mode so I can graph two functions and then see how I can find their intersection. So the two functions that I have are these two functions. So I will need to put a 1/2. Oops. And then a t squared, but it's just going to look like it's just x. Maybe I'll put a times here. X raised to the negative 1/2 power. Probably could have written this a little bit differently. And then I want 2t minus 2 should have cleared it out first. Okay. Now, when I graph this, I want it to find their intersection. So I'm just going to initially do a zoom. Zoom standard is usually a zoom fit, I think. And if it gets me the intersection, then that's what I want to look for. If it doesn't, then I need to adjust it a little bit. So I just want to find this number where they intersect. And so if I could do the trace button or even the calculate button, so second function and calculate. And then one of the options, the fifth one, is the intersection. So I'm going to intersect, find the intersection. It's going to ask me for my first curve and my second curve. First curve. First curve is y1, second curve is y2. And I have to guess, so I have to move the cursor kind of close to the intersection because it's possible that these things might be intersecting in different places. And so I want to, actually I could have left it where it is because this is just going to intersect in one place. So if I press enter, I'm going to find the intersection, and the only value that I want here is the x, which is kind of like the t value. So that's my intersection. 1.2258. So graph and then the intersection is going to be our t value 1.226. And if I go back to the graph, I can try to figure out where that is on the graph also. So I'm going to switch modes again on my calculator. So mode, back to parametric. And then, is my graph still there? It got changed again, so let me adjust the window again. I just want to move the x min, the y min to 0. So if I trace this, I can manually put in the value for t, and the value for t that I want is 1.226. And what the nice thing about this is that it'll automatically put in the x and y value. Now you can put 1.226 in for x and 1.226 in for y, and then you'll get these same two numbers anyways. So the numbers that I got from there, back to the parametric equation, your x and your y value would represent that point. And if I were to draw a line here that's tangent at that point, then it should look like it has slope 1. All right. Boy, yeah, ran out of time on that one. Okay. So what I'll do is I'll finish this up and I'll write some more notes on figuring out D, E, F, and G. And then I'll try to get that done by Friday. And then over the weekend, you can work on this, or you can work on this sooner if you want. And then see if you can come up with a solution for number 2. For extra credit, 1 point extra credit for the whole thing.
What's the scale? The whole thing? What is 1 point?
1 point for everything.
I know, but it's like, how many points is the regular homework assignment?
Oh, this will count towards your exam. 1 point on the exam for doing everything here correctly. Let's say just number 2. Just number 2. Okay, I'm going to finish up the rest of number 1. You do number 2 for 1 point extra credit. Have a good weekend.
You're going to post the rest of number 1, you said?
Yes.